right. So hopefully you can see everything okay.
Yep, we gotcha.
Oh, perfect. All right. So a little bit about me. Senior sales engineer at 7Signal. I did join back in November, but I've been in the networking space for going on 20 years plus now. So most of my time has been spent with VARs or value-added resellers or partner resellers for most of my time. But you see a couple different certifications up there, Aruba, Fortinet, Silver Peak, some fluid mesh point-to-point stuff, as well as Echo ECSE design, and then my USPAC license, which I just got back in December on Christmas Day, which is my birthday, which was fantastic. You can follow me on Twitter. I don't post much, but I actually took some time off and just recreated my Twitter a couple months ago. So at Scott I have Wi-Fi, and then my LinkedIn is listed there as well. So the agenda for today is we're going to be talking about iOS devices. What do they do? How do they function in your environment? And then what can we do to make it better? And the devices we're specifically going to be talking about are iPhones, iPads, and no longer the iPods. The iPod touches are gone. So those have been retired, but I'm sure you'll see them in your environments for years to come as people continue to use them. So this is what we're focusing on today.
Rest in peace.
Rest in peace, the iPod.
That's where the I and iPhone and iPad and so on came from, right? iPod was the first i device.
Yes, it was.
Or was it the iMac?
Oh, it might have been iMac.
Oh man,
now you're getting me confused.
I don't know. I'm sure we'll hear about it in the chat.
Oh, I'm sure. So why do iOS devices do what they do? Well, if you go out and go to Apple's website, there's an entire document on roaming and in the enterprise on how these devices actually function on the wireless. So first off, Apple devices really try to prefer 5 gigahertz. If they see an RSSI that's greater than neg 65, they'll try to attach to a 5 gigahertz network. And then based on the devices themselves and the capabilities of them, starting with the latest Apple devices, they're going to prefer AX, and then they're going to go backwards down the list, down to AC and N, and then N to A, as long as whatever your infrastructure actually supports. And then it's going to look for the widest channel possible, and then go down from there. So if you have 80 megahertz channels enabled in your environment today, it's going to prefer those over anything else. So you can kind of see how these devices go down the list when they're making decisions on the networks that they see. But the big thing to understand with this as well is that these devices trigger roaming at neg 70. So they're not going to even start looking for another access point until they hit a neg 70 dBm. So if your cell sizes are out to neg 72, it's probably where they're going to start roaming at that point. So keep that in mind as we talk through this going forward. And then as they go through and try to make these decisions when they're actually consuming data on the wireless, if they're actually sending and receiving data, they use an 8 dB RSSI differential between access points before they start looking for another one. So that can really impact your cell sizes and how your devices are going to roam inside your environment. When they're not sending data, it's completely different. It uses a 12 dB difference. So that really shows you how these devices can stay sticky on access points if they're not being busy. So it really can play havoc in your environment if you're not careful. So what kind of information can you get from an iOS device? Well, there's a couple different ways to pull information from the device itself. You have the Apple Airport utility, which is sponsored by Apple. It's out there in the App Store. You can get. There's many tools that are out there that do basically the same thing as the Apple Airport utility, but they also include some other features. There's Fring and Speed Test and a bunch of others that are out there. Not putting my name behind any of them, but if you just search the Apple the App Store, you'll find them. And then the third way you can do it is you can actually run a sys diagnostic on your device. One of the references in doing this is a website I found. It's my80211.com, which is George Stefanik has a great write-up on how to run this on your device. It's pretty involved. You have to hook your iOS device up to a Mac. You have to trigger or install a profile and do all kinds of different things. And then you end up with about 300 megs worth of data that includes everything about your device. What we're going to focus on today, though, is just the airport utility, what you're going to get out of that tool itself. And it's not much. You're going to get your SSID, your BSSIDs, the last RSSI that was seen on that scan, the channel of that BSSID, and then the last time it was actually found. And this is going to run every 4 seconds. It's going to do its scan. So it's going to go through every single channel. And you can see in the list here, I kind of took all the names out and all the MAC addresses, but you can see it's every 4 seconds that it's going to go through and scan these channels when it finds them. So it's going to go 2.4, and then it's going to go 5 gigahertz, and it's going to list them all out every single time it finds them. So you're really limited on what you can actually get from these devices, which is unfortunate because, you know, other devices that are out there with Windows and Mac OS even, you know, and Android, you can pull a ton of more data from these things. You have the capabilities to get into the operating system and pull this, but with Apple, they have it really restricted. And this is pretty much the information you can get from the device without including anything else specifically or tying it to something else to pull the information from. So besides that information, what do we want to look for in the air? What other information is important that we can kind of understand what these devices are doing outside of just the airport utility or other tools that are loaded onto the device itself? Well, over the air, we can look at different things: the RSSI, the SNR, client retries. Is it actually on the correct band? You know, when we talked about preferring 5 gigahertz, is that device actually doing that? You know, what are the data rates? How is the device actually consuming the wireless? Association, reassociation frames. How's the device roaming through the environment when it's going at that neg 70 dBm roaming trigger? Is it actually doing that? And how's it looking at the other access points in your environment? You can then look at frame sizes and understand the data that's coming from those devices. You know, is it voice or video, or is it just, you know, running just best effort traffic? We can look at that as well. QoS and reason codes. So is your environment actually using QoS? And then are you actually seeing any reasons for these devices to disconnect or have problems in your network? But all this starts with a packet capture. Okay, this is where you can get all this information from, is in a packet capture itself. It takes a lot of time to go through and pull this information from a packet capture, but you know, we have some ways to visualize it using Sapphire Eye to be able to put this into an actual graphical version, so we can actually view it reasonably without having to dig through each one of these frames and understand, hey, you know, is this a beacon? Is this QoS? What is this looking at? How do we pull all that together and actually put it into a visual representation? So the first thing we're going to look at, and these graphs you're going to see in the next coming slides are all from our Sapphire Eye. So this gives us a visual representation of all the data that's in the air that we can see that's relevant to the iOS devices and really all devices in your environment. But for this, we're just going to look at the iOS. So the nice thing when you're looking at a graph like this is you can see how the devices are actually looking from a signal strength outside of the access points and outside the clients and what's actually being seen by the Sapphire Eye. So you can see that, you know, in your environment, not specific to an AP, that you're able to have that coverage, and you can see where there's dips and valleys where these devices roam far enough away that there's no other APs, or the eyes can't see them great enough. So you can see those dips where most of the time they're pretty close to the sensors. You know, we're neg 40, which is really, really good. And as they move away, we go down to neg 82, which potentially could lead into a coverage issue if you're not fully, if you don't have enough access points in your area. Jim, you have any thoughts on that?
This is a really interesting chart because it's a really unique value we're creating here. It's not the coverage of the AP at the spot where the iPhone, we'll just say, is. It's actually the Sapphire Eye's RSSI of the iPhone as the iPhone is moving around it. So if the sensor is somewhere near the access point, you know, we can kind of make some inferences about how well the AP is going to be able to receive the signal from that iPhone. So pretty useful here, and you can tell this is definitely a client that's mobile at particular times of the day during the week.
Yeah, absolutely. And for reference as well, to give some context to these screens, this is looking at all of the sensors in a specific area, and the only devices that we're looking at in these are actual iOS devices. So the MAC addresses, which I've cut off of here, are iOS devices that we're referencing. So another thing to look at is the signal to noise ratio, which follows or should follow pretty closely to the signal strength of the device. And you can see when they roam around how that plays out through the network over the weeks as that device roams around as well. When we talk about client retries, this is indication of a couple different things with some devices. As you can see, most of the devices here that are listed, are below that 30% threshold of what we like to see in a retry rate for these devices. But you can also see there's a few of them that are a lot higher that can definitely indicate some issues going on into your environment. And Jim, what would you think on some of these that are in that 50, 60, even up to 100% ratio there potentially could be some problems?
Yeah, this is very useful, right? Because we're looking at the retried data frames for just the iOS devices in this Wi-Fi network. And each of these, although we've cut it off, for privacy purposes, each of these lines it represents a different MAC address, a different unique client. And so we can see that, there are a couple days where some devices have really struggled. Some have had 100% average retry rates for a whole day. That's pretty bad. And, we can correlate those MAC addresses with specific devices and, go investigate the history of those devices. Where have they been? How are they being used? Or has the end user experienced problems? You'd love to be able to be proactive that way. And this is a great way to get there.
Yep. So one of the other things I covered, in the first slide was, about being on the correct band. You don't really think about it too much, but when you look at this, in this case, it's just a single device, but that could definitely affect, depending on how the design of your wireless is. If you have a device preferring 2.4 over 5 gigahertz, why is it doing that? Why is that client making that decision to be on 2.4 versus 5 gigahertz? Is it a coverage issue? Is it not meeting those thresholds set by Apple? And you can tell that, there's multiple devices over the different week, over this week that are actually doing that. So there's a specific area where these devices are actually choosing 2.4 over 5 gigahertz. And if they're running, a high volume application, or you have a lot of interference on 2.4, then, this client can definitely suffer. So having the ability to understand that your devices are not where they should be can lead you down the path of understanding how your design is working, and then what are your access points doing there. So it's a nice, insightful piece of information.
Yeah, that's a really useful graph, because if you see a lot of dual band clients in 2.4 gigahertz, that suggests maybe there's some design improvements you could make. If you see one or two, or in this case, really looks like one that's there most days, you might want to go see where that client is, where it spends most of its time, and look at the, maybe a localized design change, for example.
Yep. Now we get into the fun data rate slides. These are the ones I really like, because you actually get to visualize how these devices are using the wireless. So in this instance, it looks pretty good. I mean, you see 32% of the time it's at 6 meg on A, which if you look at it could potentially just be data rates, or I'm sorry, management frames. But you also look at this and you see, 27, almost 30% of the time it's at 300 meg, but it's an end device. So it's an older device that's on the network, but you can see that it's using the upper end data rate. So it's using the most of its capabilities while still, potentially running all its management frames at the lowest data rate, which Swamas talked about in his webinar last week, which was kind of neat. So, this is a good example of how this device is actually performing well in the network. The next one we look at is definitely not doing that. And you can see, because a lot of the MCS rates that you see on the lower left are MCS 0 and MCS 1. We have a lot of slow data rates, even though it's using AC. This to me kind of points to a coverage issue, because we have data rates all over the place. You see a percentage at 540 at MCS 8, but a majority of the time it's MCS 1 and 0. So what is that doing? And with this information, sorry, go ahead, Jim.
Yeah, I was just going to say, coverage, roaming, interference, co-channel interference, for whatever reason, that the quality of that Wi-Fi link is degraded quite often. And so it's rate shifting significantly. So that's like you said, one to investigate for sure.
Oh, absolutely. So now we get into a couple different things. So we start looking at authentication and reassociation frames. In the authentication, you can see that, if you have devices that are there all the time, they should just be connected if they're not leaving the network. But as they join and leave, you're going to start seeing authentication frames coming through. These devices are actually coming on and off the network. In this case, it's pretty stable. Everyone's staying on there, but there's a few of them that are bouncing on and off. If you're seeing a ton of association frames, you'll see those peaks and valleys as people come in and out of your network, which means, it's either working as it should be. But if you localize this to specific access points, you may be on the fringe edge where you have devices actually dropping off the network specifically. So it's a good way to understand that your devices are staying on the network, or there may be potential where it's bleeding out of your network and devices are trying to connect to it. The next one is reassociation frames, and this is really how you can tell how your devices are moving in between the access points. So this is a good and a bad thing. So depending on how your devices are moving, if you're expecting a lot of roaming in your environment, you can see the amount of frames that are going between those devices and understand that they're actually making those decisions between the APs. Now, if this is an extreme amount where you start seeing this one device, at 12 frames per minute, it might be bouncing between cells. There might be multiple, it might be sitting on a cell edge where it's making a bunch of different roaming decisions between access points. There may be something wrong with that. So you can take that MAC address, take it back to your environment, look at it and say, okay, what's actually happening and where is this at?
Yeah, this is useful. It definitely needs some context. You have to know if the device was mobile or not. But if it's not, and we see a lot of reassociation requests going on, then maybe something's going on there that needs some additional troubleshooting.
The next ones we're going to look at are frame sizes. This is kind of cool because you can kind of start to visualize how these devices are working in your environment. We're going to look at both sides, the download and upload. So on the download side, you start seeing packet sizes, creep up where there may be voice and video going on. So that's going to play into another couple slides here where you can start visualizing performance indicators. But as the packet sizes go up, as you see this red line here, go up to 1,500 bytes per frame. I'm sorry, not packet sizes, frame sizes, up to 1,500 bytes. You start to understand that this might be voice and video that's being the primary traffic might be voice and video across this. And then we look at the upload side. In this case, we know where this device is at. You can see that the frame size is actually over 2,200 bytes. So what could that indicate? Well, it's, some Apple services might be in play here. Apple TV, Apple Play, AirDrop, something along those lines that could be utilizing a larger frame size that could, potentially show you how these devices are consuming the wireless. Now, talking about that with voice and video, the other thing we can see as well as QoS. When we start seeing the different QoS markers in the wireless and understanding your infrastructure, if you're seeing devices actually mark this traffic on your wireless, you want to validate that your infrastructure is actually configured the same. So we see this here. You see best effort at 3 and voice at 6. You can see that this specific client, is most of the time is probably doing web traffic, but a lot of the time it's actually spent on voice calls. So if you have Wi-Fi calling enabled, if you're doing a lot of, things like this, you're going to see a lot of that marked traffic. You want to be able to validate that your infrastructure is actually configured the same to be able to interpret the QoS markers and be able to pass those along through your infrastructure. One of the other things we can look at is reason codes. And the nice thing about this is that when you get into the actual, into the reason codes, you can see, in this case, we have reason code 17, which is a 4-way handshake error, which potentially in this case is a PSK network that they might actually just have the wrong PSK entered into the network. So we can see these devices are having problems connecting to the network.
Yeah. Yeah. And we can see other status and region codes as well. And of course, deauth frames as well. And Stefan made an interesting point in the chat about how iOS will actually blacklist an SSID if the device, and I believe that might be a BSSID, if the device has received more than 2 deauth frames within a 5-minute period. So definitely something to keep an eye on. A lot of, the more advanced features from AP vendors involve actually intentionally deauthenticating clients, and iOS often can react poorly to that. And Stefan clarifies it is actually an SSID level blacklist. So
Oh, wow. Okay.
something to keep an eye on.
Absolutely. Thank you for that. So what can we do to make it better? After looking at all those slides and understanding some of that data, what can you do to make your wireless network better? Well, one is to validate your design meets the requirements that set by Apple. Does it meet the roaming thresholds and the signal strengths that are required? Follow your vendor's guides for deploying Apple devices in your environment. Every vendor pretty much has one out there. I'll reference a few here in a minute. And the next one is enabling advanced wireless features. So there's some things we're going to talk about, but make sure you take this with a grain of salt and you understand before you implement these that, you validate that all these are going to work in your environment. So it's not one size fits all. Every environment has its own little, their own different devices that may or may not support them. And there's also iOS levels that you need to adhere to make sure some of this stuff works. So make sure before you deploy this in your environment that you do the proper testing and make sure it's going to work. So for the Apple design requirements, I listed a couple different links here that we'll put in the chats. Cisco has a great best practices for iOS and Mac in the wireless environment, and it's very detailed on all these things. They list everything out for you. Aruba has the same thing, and it's specifically more around the AC environments for this link that I provided. And then Apple has a bunch of different guides on roaming for the enterprise. So you can follow these links, go through, read what's going to be specific to your wireless environment, make sure that you implement them correctly, and you make sure they're not going to impact any other device outside of the iOS ones negatively. But some of the advanced features we can start looking at, and these are the ones I want you to be careful with because they may, you need to do your research, but 802.11k, 802.11v, and 802.11r are three advanced wireless settings that you can enable. 802.11k is going to be our AP neighbor list. So it's going to present that to the client so they can understand when they start doing their roaming, it's going to say, hey, we have access points on these channels, scan these first and understand where these APs are going to be so they can, instead of not having that enabled, it's going to have to go through, scan every single channel, then figure out which one's best and then go through it. With the AP neighbor list, it's going to present it. And then the client's going to be able to make a decision off of that a lot faster. And with the Sapphire Eye, we can look at the SSID or the SSIDs and BSSIDs specifically and validate that these features are actually enabled on the SSIDs.
Yeah.
802. Sorry, go ahead, Jim.
Yeah, and Apple has said that 802.11k neighbor reports, those are the first channels an iOS device will scan when it does off-channel scanning. So definitely a very valuable feature to use if you can, if it's not disruptive to other clients in your Wi-Fi network.
Yep, absolutely. Next one is 802.11v. So this is a BSS transition management. So the fast transition. I'm sorry, it's BSSID transition management. And then I listed out some links here so you can validate all these different features from the IEEE as well. We'll provide all these links so you can read them in depth if you like. And then 802.11r, there's a couple different modes that you can run with this. There's there's on, off, and adaptive. I believe you need iOS 10 or later to take functionality of this, and there's specific codes, I think even in Cisco, that support this. I think it's 8.3 and above or above, I believe, but I'll have to validate that for you. That is also going to help with pre-authentication, especially when you're using 802.1x networks, so that the devices can pre-authenticate against the next AP it's going to roam to, so that it takes it from seconds to milliseconds for the transition between APs. The other part we can look at is we talked about QoS. We want to validate that QoS is actually configured and running on your SSIDs, and we can look at that as well through Sapphire Eye and actually see what categories are configured through WMM. And there's a bunch of different guides out there for Cisco. There's best practices from Apple. Every vendor out there has them. I just listed a couple so that we could see them. But you want to validate that this is configured, and then not only on your wireless network, but on your actual infrastructure, your networking itself. It has to be end to end to make sure this stuff works. So it doesn't end at wireless. It continues on throughout the network. One of the other things you want to look at to be able to fully utilize all the services with iOS is MDNS or Bonjour. So this is your Bonjour gateway with Cisco or Aruba Air Groups to be able to use Apple AirPlay or AirDrop, those type of applications, AirPrint. You can also pull this information out of a packet capture to validate that it's actually functioning. But I also listed some guides here to follow. They're very in-depth. There's a lot to go into them. The configuration is not super difficult, but there's a lot of parts and pieces that have to be configured to make sure it's working correctly across the network, especially between inter VLAN working and everything else. But this is a good starting point to make sure you can look at that. And the last one I want to touch on is design. It's not a feature, but it is. You have to have a properly designed network to make sure that all these things that you implement are actually going to work across the network. This is probably the most important thing in my mind for devices to work in any environment is a proper wireless design. This will alleviate a lot of your issues that you're going to see, but to me, this is probably the most important. Jimmy, have any thoughts on that?
No, you're right. I mean, and it's, the hard truth is we don't have any nerd knobs in iOS we can tune to adapt an iPhone or an iPad to our own Wi-Fi network so that it, works better for, with the existing designs we have. If we want to improve their performance, we have to live with the way they behave and adapt our networks around their behavior. So that's where those design guides from the different vendors that Apple has helped generate are really valuable.
Absolutely. And that's all I got. So hopefully this was informative. If you have any questions, throw them in the chat. I'll try to review them as we go on, and I'll pass it back to you, Heather.
Yeah, and let's do a little bit of Q&A. We had some good comments come in. A lot of people asking about where we got those numbers and characteristics about how iOS roams. And so we've shared that link a few times to that web page.
Perfect.
That Apple's published.
Thank you.
Chris, we have a question from Chris, and Chris Kelly asks, do the roaming behaviors apply across the board for all iOS devices, or does the behavior differ by actual device type? That question.
That is a good question. I will have to go back and validate that. All the referenceable material that I saw some of it did apply between macOS and iOS specifically. But there's also different versions of iOS that are supported that have, I believe there's the versioning in there between the actual OS version. So let me follow up on that, and I'll send you an email with a follow-up on that.
Yeah, and I think my take is, Apple doesn't publish that there's any differences. Now there are some feature support differences in different hardware and OS levels, like 802.11 kVNR, like we mentioned. But I wouldn't be surprised if there were differences in roaming between different hardware levels that are just unpublished, and you kind of have to find out by testing devices in your network specifically. I will say, I think there's a lot more to the iOS roaming algorithm than is publicly shared by Apple, an awful lot more.
I will agree with that.
And sometimes you're left kind of scratching your head, sort of trying to, make sense of the behavior you're seeing and what you expected to see. So yeah, as always, if it's really important, you've really got to test it in your environment for sure.
Yeah, absolutely. And the list that I provided, that's just a brief summary of what you can look at for an iOS device in the network. But there's many more other KPIs that you can view to make sure that the devices are doing what you're expecting them to do. So